Work and energy. Work is done when a force moves a body through a distance in the direction of the force. Work is equal to force times distance covered in the direction of the force. The unit of work is the joule. If a force acts on a body and moves the body through an angle theta to the horizontal as shown below. Here's the force acting on the body and moves it through an angle theta covering a distance d meters. The work done is W equals to force times distance times the cosine of the angle it's made with the horizontal. Energy is the ability to do work. It exists in different forms. The energy of a body at rest or at a height is the potential energy. Potential energy PE is determined by using the equation potential energy is equal to mass times acceleration due to gravity times height. The letters are explained and shown below. The energy of a moving body is called kinetic energy, KE. The kinetic energy of a moving body depends on 1. The mass of the body. In fact, it's directly proportional to the mass. The velocity or speed of motion of the body. Kinetic energy is directly proportional to the square of the velocity. The formula for determining kinetic energy is half mv squared. M for the mass, v for the speed or velocity. The formula for determining the kinetic energy of a body is half mv squared. Ke is equal to half mv squared, where m is the mass and v is the velocity or speed of motion of the body. Example 1. A constant force of 40 Newton acting on a body initially at rest gives an acceleration of 0.1 meter per second squared for 4 seconds. Calculate the work done by the force. Option A, 8 joules. B, 10 joules. C, 32 joules. And D, 160 joules. The solution is as follows. We are given the force as 40 Newton. Initially at rest, that means the initial velocity. The body was at rest is 0. We are also told that the acceleration is 0.1 meter per second square, and it lasts for a time of 4 seconds. To determine work done by the force, we need the force and we need the distance covered by the body, because work done is force times distance. So first we have to determine the distance covered by the body. Using the equation of motion, D is equal to ut plus half of at squared. In any case, D here is being used to represent distance. D will give me 0 times time taken 4 plus half of 0.1 times 4 squared. The distance covered is equal to half of 0.1 times 16. That will give us 0.8 meters. Therefore, the work done, which is force times distance, is given by 40 times 0.8, which is 32 joules. Option C is therefore correct. Example 2. A body is under the action of force such that the force displacement graph of the body is semicircular as shown below. Here's the semicircular description. The work done on the body by the force in moving through 24 meters is dash. Option A, 36 pi joules. B, 72 pi joules. C, 144 pi joules. And D, 288 pi joules. The solution to the problem is as follows. For a force displacement graph, the work done is equal to the area of the shape under the line or curve obtained in the graph. Our shape is a semicircle. Therefore, work done equals to the area of a semicircle. Area of a semicircle. So work done will give us half pi r squared. Our radius will be 24 divided by 2, which is 12 meters. Therefore, work done will be half pi times 12 squared. The work done will be equal to half pi times 144. Therefore, the work done is 72 pi in joules. Option B is the correct answer. Example 3. A car of mass 200 kilogram left a town S and reached a town T when its speed was 360 km per hour. Find the maximum energy of the car before it finally came to rest. Option A, 7.2 times 10 raised to power 4 joules. B, 1.0 times 10 raised to power 6 joules. C, 2.4 times 10 raised to power 6 joules. D, 13.0 times 10 raised to power 6 joules. The solution to the problem is as follows. What are we looking for? We are asked to find the kinetic energy because the car was in motion. Kinetic energy, you must remember, is half mv squared. We are provided with the mass as 200 kilogram, the speed of motion 360 kilometers per hour, this speed must be converted to meter per second. So to effect this change, 360 kilometer divided by 1 hour is the same thing as 360 times 1000 meter divided by 3600 seconds. This will take off this will take off this, 36 will take off this. So 360 kilometer per hour is the same thing as 100 meter per second. Therefore, kinetic energy, which is half mv squared, becomes half. The mass is 200, the speed is 100 squared. 2 here, into 200 will give us 100. So we end up getting 100 times 10,000 joules. The answer is 1.0 times 10 raised to power 6 joules. Option B is therefore correct.